Welcome to the demo session of the course FPGA based signal processing system. So today's demonstration session we will be doing a small program to read the file in Vivado, how to read a text file in that, and after that we'll move it to CORDIC in simulation and their hardware implementation. So let's start with the small program. So I'm just opening that program, it already created. We'll open the XPR file. We are using 2025.1 Vivado ML edition it is. Subdating now done. Just have a look. So I've created a module named file read. Now this is the important part, that read memory. I just save the data.txt. You can check that data.txt having the data 00000010 like that. And I have given the path over there in this read mem. This is the path of where I just save the data.txt file RAM in this. So this is the command in which you are going to read your text file in the Vivado over there. Now I'm moving from I just initialize the I is equals to 0 in the for loop itself. It will be running to less than 16 minutes. It will go up to 15, 0, 1, 2, 3 up to 15, and it will increment that I every time I is equals to I plus 1. It begin address, it will check the address for that. For every 50 nanosecond, it will be doing the same thing. It will be running the for loop over there. And after that, we'll display the data and RAM address over here in the TCL console, right? It's a small program. So if I run the simulation, click on the run behavioral simulation, you can check that. Okay, now see, this is the RAM. In that you can check the data over here. It is like in the first place, it is 0000. It's again 0010. You can verify the data. We have just read that file in the Vivado. This program can be used in the memory block design where you have a data from a text file that can be stored in the memory, and after that you can extract the data by using that memory code itself. So we'll segment the data into a small, suppose it's 16-bit data, we'll segment into 4 parts like M0, M1, M2, M3, and we'll save that M0, M1, M2, M3, we'll vary the address and we'll retrieve the data from the memory block. This can be also done if you are taking the data from some ADC and DAC. Over there you can store the data in the text file, and that data can be read in the Vivado by using this program. So in multiple ways you can use this file read program. Now moving to the next program. So we'll open the CORDIC. So I'll go ahead with the XPR file, click on OK. I'll close the previous one. So let's move ahead to the program. Now if I open that CORDIC, so the function name I just given it the CORDIC sin cos theta. Now this cos theta and sin theta I have to store somewhere. No, the output can be shown somewhere. So cos theta I am storing in the 16-bit. So it is a sin 16-bit, 15 to 0 means 16-bit cos theta, and that's a sin theta, right? Now since the 30 degree we have to store it somewhere, so I am initializing a local parameter over here. It's again a sin 16-bit number, angle 30 degree, it is on 16-bit of decimal 9830. Now where this 9830 comes? So if I convert the 30 degree into radian part, it will be like pi by 4. And now if we convert into Q 1.5 format, 1.5 format means it will be 16-bit format having first bit as a sign bit and 15 as for data, right? So it will be 2 to the power 15. So every time we will multiplying the angle with 2 to the power 15. So it will come like that. So for 30 degree it will be pi by 4 multiplied by 2 to the power 15, it will come around 9830. So that 9830 we are storing as angle 30 degree over there in the local parameter. Clear? Again, for that k value, that k is 0.6073. So I am going to multiply because we are going to convert it. Floating we cannot give. No, we have to convert it Q 1.15 format. So again, it going to multiply by 2 to the power 15. So 0.6073 multiplied by 2 to the power 15, it will come around 19898. So this two value I am going to store in the local parameter having angle 30 degree and k value, right? Again, we have to store the angles also. For every angle that in the lookup table, we have to store that. So I have created a table having the value of 45 degree, again moving to the 26.6, 14, 7.1, 3.6, 1.8 like that, okay? So this value can be converted into radian. After that, it will be multiplied by 2 to the power 15. So the corresponding value will be stored in the table, like table 0 having the value of 45 degree, that is 14746. Similarly for 1 it will 7833, like that we have stored, so that it can be extracted. Now I have created 3 internal resistors. First it will having 3 16-bit register that will save the intermediate value of x, y and z during the iteration. So x will be again the 16-bit, y will be again the 16-bit, z is also for 16-bit. So this register will store the value of x, y, z during each iteration. Since I am defining the 3 states, so idle state and for second will be run and third will be done. After completion it will give the done one. Idle will be 0, run will be 1 and done will be 2. So this state can be identified by the 2-bit itself. So I am giving this 2-bit state 1 colon 0. So state will be of 2-bit, either is 0 0 0 1 1 1 and 1 0, right? Port 0 0 it will be in idle, port 0 1 it will be on run state, and again port 1 0 it will be in the done state. Now we'll initialize the value in the always block. Either it will run with the process of the clock, rising edge of clock, or the reset. It will start. The initial value of x will be k, by is 0. It's a decimal value of 0, 16-bit. Angle 30 degree we had already saved over there in the local parameter. You can check that angle 30 is there. And I, it will start from the 0, right? So it will be going to the, after initializing, will be going to the run state, right? It's rising edge of clock, we will move in from I0 to up to 9, right? The same way, x and y, it can be like updated over there. You can see that x and y is updated, and z we are taking it from z minus the value we have stored in the table itself, right? After that, after 10th iteration, it will check the incrementation. If it's not done, it will store the value. So x will be giving the value of cos and y will be giving the value of sine over there. X will be cos it and y will be this. And after the finishing of this loop, it will say that, okay, our program is completed. It will give in the state as done and will hold the result, will end case, end module. This is a simple program that can be used to compute the sine theta and cos theta from the CORDIC algorithm. Now if I simulate it, if I have just written the simulation file for that, it's small. If I open that, with every 5 nanosecond, clock is equal to negation of the clock. So it will be of 10 clock period. So in the display, you can check that I am displaying the cos theta and sin theta. Cos theta will be 30 degrees, sin theta. Initially, it will be in Q1.15 format, means the value is multiplied by 2 to the power 15, first bit for sine, and similarly for sine also. Now after that, we have converted it into the cos. How will we convert into actual value? It should be divided into 2 to the power 15, right? Because the output we are getting x by, it will be multiplied, it will be in the Q1.15 format. So the value itself is multiplied by 2 to the power 15. So for the actual value, we have to divide it by 2 to the power 15 value of that one. So if I run the simulation, run the behavioral simulation, the output you can check that for cos it is coming up around 29013, and for sine, if I convert into the binary itself, you can check that radix binary, it is like that. We have to convert into decimal, we'll convert the sine decimal over there. Okay, you can check that value. So for the cos, it is coming around 29013, and in sine it is coming 15228. Now if I see the TCL console output, it is running up to 100 nanosecond. So cos 30 sin 30, it is in the Q 1.15 format over there. If we convert it, it will come out cos 30 degree, it will be 0.885406, and sin 30 is 0.464722. This is the approximated value. You can get it from the simulation. So this is all about CORDIC simulation. Now we want to implement this on the hardware itself, on the ZedBoard, how it will run. So the problem with this one, that we are in this program, we will be using the 16-bit, right? But for the board, it is like we cannot give the 16-bit over here because we have only limited resources there. So we have only 8-bit as input, 8-bit we can see as output. So I have converted this program into 8-bit. Of course, resolution it will decrease, but we can see the output itself. We'll open CORDIC I have already created. We'll open the XPR. We'll close the previous one. And then we can save it. Okay. Now moving ahead, it's updating. You can see that if I open that CORDIC, cos 30 degree, since I have again that same program itself, only the change is, since in that previous program we are using the 16-bit, and in this program we will be using 8-bit only. For 16-bit, we are converting into Q1.15 format. So every value, it is multiplied by 2 to the power 15 in the previous case. But in this case, since we having limited 8-bit, so we will be multiplying it by 2 to the power 7, the first bit itself for the sine bit. So see, the output I am taking at cos, so it will be of having 8-bit. Now angle 30 degree, it's not the previous value, it's updated. It will be 0.5236, that is pi by 6, multiplied by 2 to the power 7, that will come 128. So it will be 67. Similarly for K value, it will be approximately 77. Again, in the same lookup table, you have to store the value in the Q like 1.7 format. So again the same state, and we have defined the XY intermediate state is also of the 8-bit itself. So XYZ state will be changing from this because we are going to move it from 0 to 7 itself. So we need only 3-bit over there. So 3-bit is there. State idle, run and done. It is in the 3 stage, so 2-bit will required, it is over there. And always it's the same thing, but only change we are making it after getting the value. So we will be getting the sin theta and cos theta itself in the same program, right? But we have only 8 LEDs to show the output. So I just commented out the sin theta part. This will give only cos theta. So the all 8-bit in the ZedBoard we will be using for cos theta. So cos theta will be the X value. It will give the, by seeing the LED, we can check that what is the value of cos theta over there. Now it's hold the final output, it's in program. Now if I open the constraint file, you can check that these are the package pin we are using. It is corresponding to the LED on the ZedBoard. All will be running on 1.8 volt of logic. That IO standard, you can see that clock I am giving it from by 9 pin, and for reset I am using the N15 pin. This switch, this push button we are using for reset. So I already created the bit stream. I'll just dump into that. We'll open the hardware manager, open the target, auto connect. Now you can see that board is getting connected. So you can see that the output is now on the board itself. The output you can see that like value of cos theta. So if you convert it into, this is the binary one, no? So if you convert it, it will come like binary to decimal, it come 111. This value is in the format of Q 1.7. So if you convert that, it will come around, it will be divided like 111 divided by 128. So the output will be, it's exactly, it will be around 0.86718. The exact value of cos 30 degree, it will be 0.860, no, 0.8660, but it is coming 0.86718 over there because we have reduced the resolution also. On the board, we are using only 8-bit over there, so you can verify the output. Similarly, you can check for sign also. So in that sign only, the change is, if I open that sign XPR file, the change will be in this state, right? In the constraint file and in the final output in the code. Like if I open that, no, in place of cos, it will be sign now. Again, it will be for 8-bit itself. Rest will be same. And the output now, I am commenting out the cos. We are taking the by value itself only, right? So in the constraint file, if I go there, so it initially it was for cos. Now it will convert into sign. All will be running with 1.8 volt of logic. Again, by 9 for clock and 15 for the reset. Clear? So since I had already created, I'll just open the hardware manager and we'll dump our code and check the output. Let's check the output. Okay. It is programmed now. We'll click on program device, program. Now just check. These are the MSB, this is the LSB. So it will be coming like 001111111. So if you convert it into binary, it will come 63. So again 63, it will be in the format of Q 1.7. So you have to convert into the actual value. So the 63 will be divided by 2 to the power 7. It will come around 63 divided by 128. So approximately it will be 0.5. It's not the exact. It will be like approximately 0.5. In this demo, we have seen that first how to read a file in the text file stored somewhere in your computer in the Vivado program. Second, we have implemented the CORDIC. CORDIC initially for the simulation I have taken 16-bit and we have executed it for 10 iteration and get the output. Output was not exact, but it's approximate. It will have some error, right? Because we have converted the trigonometric function into the only addition and the shift operation, right? So for every iteration, it will have 1 shift and 3 addition, and the one lookup table we have to be used to store our theta value. So we have converted that code into 8-bit. We just implemented that code in ZedBoard and we'll check the output. Either we are getting the exact or not. So for the cos, it came around 0.86 something, and it's a small error also. And for sine, it is like 0011111. So it's 63 divided by 128. So it's approximately 0.5. Thank you.